everyone. Welcome back to our YouTube channel, Becoming a ROS Developer. My name is Rodrigo, and today we have one of our students, Marcio Costa, who has completed the course ROS Basics in 5 days. And in this course, there is a project at the end that you can come and present here with us, and it's actually implemented on a real robot. So that's what we're going to be seeing here today. So, hello, Marcio, how are you?
Hi, I'm doing fine, and you?
Great. I'm excited to see your project. So please, whenever you want, start sharing your screen and show us what you've done and how you've been able to do it.
Okay, I'll share my screen. Just give me a moment.
You there? Hello, hello? Oh, it seems like I can see myself double here, so let me switch. Seems like we had a disconnection. Oh, I can see him trying back in, so let me let him back in. Hello,
Hi,
Marcio?
that's the connection, sorry.
All right,
Uh,
cool. You're back online. So you were about to share your screen and begin the project.
yes, can you see my screen now?
No, I cannot.
Just a moment, you should
Now
be
I
able
can
to
see it.
see
Awesome.
my screen. Okay, so this is the project, right? We have a robot, we have the environment, and we have to make the robot follow a wall. So I will just run it, show it to you guys how the robot behaves, and then I'll
Please.
explain all the project, okay? Okay, so first the robot will find the wall, it will rotate, and when it will come close to the wall and then will align the wall to the right, and then it will start following the wall. So right here, on our, you can see the driven distance and what the robot doing. Right now it's steering left, now it's going forward, steering left, and the distance increases.
Nice.
You can see, yeah. It's a little bit slow.
No, that's good. Very
Yeah.
smooth too. Looks like, do you have a controller in there or is it just if else?
Yeah, I implemented some. I didn't like the how the robot was behaving, was doing some lines when was following
So
the
you did a little bit of extra work. That's awesome.
yeah. I was not happy
Great.
with the movement, so
We
I did
always
a
like to see improvements. So then we have a driven distance there, um,
yes,
which I'm assuming comes from the action, right?
yes for the
Okay.
odometry node.
Oh, and then it
Then
stopped.
it stops and it returns the all the coordinates.
Cool, cool, cool. Great. That's the project in
Yes.
really quickly. So, could you please explain us how you've achieved this? Looking at the three main parts of the project.
Yes. So I have here something to show you.
Oh, great. Awesome.
So we have three nodes, right? We have the wall follower, the find wall, and the odometry. And the wall follower will ask for the service server find wall to find a wall. The find wall node will find a wall. This will actually rotate and look for the minimum distance that it finds and will come closer and then align the robot to align this object that is found to the right of the robot. So it should be a wall, I assume. And then it will return to the wall follower. Look, I have found the wall. And then it will start following the wall. And at the beginning, before it actually start following the wall, it will ask for the odometry action, server actions, to start recording the odometry.
Mm-hmm.
And the odometry will provide a feedback with the driven distance to the following node, to the wall follower node. And the robot will do a full lap, right? Because it's following the wall. And the odometry node actually knows where the robot started. So when the robot comes close to that spot, it will stop and give a response to the wall follower and saying, look, you've done a full lap. Here's the list of coordinates that I have recorded. And the wall follower will stop the show, will stop everything. And as we could see, we will receive the list of coordinates. So we should jump back to the code, right? So I can show some code of what's actually happening here. You have any questions?
Not yet. Please finish your presentation, and I'll ask you a question.
So when the wall follower node starts, it will call the find wall action, and the find wall action will actually call the service action, the find wall. And here's the callback for it. And when we go to the find wall, when the node starts, we have this logic right here. That is what actually finds the wall. We have a couple of steps here. As you can see, it starts with wall found wall false. I have some cache mean distance for the logic, and the first step is step 0. So at step 0, we actually want to put the minimum distance of the lidar at the front of the robot. So it will just rotate. That what happened at the beginning. The robot was rotating until the minimum distance that the robot senses is at the front of the robot. If the minimal distance is in the front, we'll go to step 1. In step 1, we want this minimal distance actually to be below dot 25. And that's when the robot comes close to the wall. And when the minimal distance is below dot 25, we can go to step 2. So step 2, the robot, we have to align the wall to the right of the robot. So the robot will rotate again until the wall is at the right of the robot. After that, it will provide the feedback to the wall follower saying, look, I have found your wall, and we'll call the callback will be triggered, the start following function. So what happens here? When the start following actions is triggered, we have this action record odom that will call the odometry node, the action server, to start recording the coordinates. After that, it will subscribe to the scan, that is our lidar, and we'll start to follow the wall. So we can, since we call the odometry action, I think it's fair enough to we go see what's happening here. So this is the odometry. It's an action server, and it subscribes to the odometry topic to receive all the data. So real quick here, we can see here the logic behind this. So this actually run each second. So we have a delta. A delta is basically the difference between the initial position and the current position. So we can know what's the difference between the two positions. And we'll calculate this distance and provide this feedback to the wall follower. So back to the wall follower, we have here our code to follow the wall. Let me just close this so we can have a better look. Okay, we'll trigger the follow wall as a callback. And the follow wall callback is this one right here. We can see all the logic that makes the robot follow the wall. So I have here some variables, moving away from the wall too close, and is wall far enough. I use this to help me make this smooth lap that the robot makes.
I see.
Yeah, so thing first, we're going to look forward to see if we have any obstacles. So if any obstacles is at a distance less than dot 4, it will make a, a left turn, a sharp left turn, let's say. That happens when we are at the corners, basically.
Yeah.
Otherwise, it will check. Is the wall far enough and is moving away from the wall? And if the wall is far enough and we are moving away from the wall, we want to steer right, so we don't go too far from the wall. And we have another condition here. Is the wall too close and we are not moving away from the wall, then we want to steer left, so we go closer to the wall. Otherwise, we just move forward. That's the basic concepts right here. So it will be here in a loop, right? And here at our odometry node, we can see that when we have the distance between the current position and the initial position, when the delta is less than 0.18, we will push the list of recorded coordinates to we'll send a response to the wall follower node, basically.
Mm-hmm.
And yeah, this is basically it. When we receive this response, a callback will be triggered and we'll stop everything.
All right. Awesome. Is
Yeah.
that it then?
Sorry?
Is that it then?
Yeah.
Okay,
If you
cool.
have any questions, I can try
Thank
to
you
answer.
very much, Marcio. Very nice, very straightforward, and a successful project is always nice to see. Um, it. So I do have a couple of questions.
Mm-hmm.
Um, First, I said like the smoothness of the movement. It's real
Yeah.
nice considering you're just doing four if statements. Because we can implement like a controller. I thought you had like a PD controller um, from the way it was moving, but I'm assuming now I see that a couple of if statements, if that does the job, then that's great, and it's good practice to make it as simple as possible, in my opinion. So you talked about the first thing I want to ask is so if I understood correctly, you have a callback. You call the service uh, from the wall follow,
Mm-hmm.
and then it does the server callback and whatever, and then it comes back to wall found, and then another callback is called in that wall follower to start moving.
Yeah, basically when the find wall sends the response that the wall has been found, it triggers a callback on the wall follower.
Okay, and then the movement starts.
And
So that means you have more than one callback in all three nodes.
in all three nodes. No, I have all the callbacks are in the wall follower. Yes, I have to
Yeah.
have some callbacks
Well,
in
you
the other.
must have
Yes,
two
yes,
in the service server and two in the action server.
yes.
Which ones would those be? The callbacks of the service server, for example. So the first one, which one
Yeah.
would that be?
Okay, so we have this is to handle the service. This is when a request is made.
Yes, which is the server callback, we call it. Every
Yeah,
time you call that, and in the other side, you have odometry callback. Basically, you're subscribing to the odometry, you're doing things. The reason why
Yeah.
I'm bringing this up is first because you obviously had to deal with multi-threading, to be able to handle both callbacks in callback groups. Uh,
Yes.
so then something I did notice, which is an advice. I saw that in, I forget which one it was. I think it was the Fine Wall program. You have your scan callback, and in that scan callback, you do everything, right? Is that correct? So I see that scan callback is up there,
Yes.
and then you do all that processing,
Of
which
finding the
includes the publication of the command vel messages, right?
yeah.
Yes. So
Yes.
I advise against that, and
Oh,
here's why. So when you do a sensor callback, you wanted to do it. You want to do it as simple as you can. Why is that? Because that callback is gonna get executed every time you get a new message, a new LiDAR reading, and uh, of course you lose that message.
yeah.
And of course, in here it can go fast enough that might not be a problem, or the application is simple enough. But once you start getting into, obviously you want to take advantage of all the readings that your sensors are giving you. And so you want to try and avoid that. And especially like, I don't know if you're creating the publisher. I don't think so, but like sending publishing, that means, that RCL CPP is communicating, with the libraries, and then sending it to the DDS network, and then making that publisher, and it's just going to add on to it. So my advice is to just extract the message, maybe extract the front, the right, and the left, and then you do things somewhere else. So that way you can at least always get that
So
value.
I don't publish at the same rate as I'm reading the LiDAR. Is that it?
No, you do. You would in fact make be more sure that you can publish based on each received lidar scan message.
Okay. Because I'm creating here the publisher, right?
Yeah, yeah.
And to each moment.
So I would publish it out of that callback,
Okay.
and then the last thing I wanted to talk about is what happens, the classic one, and how would you improve it? It's not part of the project, but I always like to ask it. What happens if you're too close to an obstacle, and how would you fix that?
When the robots start moving or during the wall following
Yeah,
procedure.
when you launch everything, what happens if the nearest thing is not the wall, but an obstacle?
Yeah, actually that is a problem because we are the program of the algorithm was made to a specific scenario where the closest object will be the wall. Otherwise, if it picks some obstacles, it will think that that's the wall. So we'll face that obstacles and try to align the obstacle to the right, thinking that is a wall, but it's not. So how could I improve that?
Mm-hmm.
Basically, I'll have to know if that what I'm sensing, what the robot is sensing is a wall. I'll have to make some algorithm or something to make sure that this is a wall.
Yes, and remember, the simplest is the best. And let me tell you something, because I saw that you're already taking ranges of lidar values as your right value, to make sure it's not just one, I'm assuming, because you took like,
Mhm.
I saw like 20 points or something. So you already have that mindset of taking your lidar in sections, right? So like
Yeah.
in sections. So what I would do, for example, once you like you call that service. And again, like this is not part of the project, but I always like to talk about these things, to get ideas and to solidify your
Mhm.
understanding. So you detect what's the closest point, and then you take a range. What
You
range? Well,
left.
let's see. The obstacles are really tiny, so most likely that they won't take up more than, I don't know, five lidars, even if you're really far, really close to them. Sorry, even if you're really close to them, probably they won't be bigger than 5 points because it's a little stick, so it's really short. So let's say, all right, I get my smallest value, then I take that value and look 10 to the right and 10 to the left, and then I look at those values. What you can do is just take the standard deviation of those values, right? Because if they're not all, if it's an obstacle, then that means one of them will be, that stick, and then the other one will be all the way back on the other wall, right? Or, whatever else is back, which means that standard deviation will be big. And then if you're looking at a wall, then that standard deviation will be small. So that could be like in 2 lines of code, you can do a little filter to check, hey, like here's my closest. Let's look at the range. Does it fluctuate a lot? No,
Yeah.
then that means it's the wall. Does it fluctuate? Yes, then that means it's an obstacle.
Not the wall. Yeah.
So I just wanted to mention that because I see that you're almost there, and so for your future projects, I want you to always think of how you can generalize it more and more. Of course, there's a point until you can't do it because you're doing something for an application. But that's what I wanted to mention because I see that you're almost there. You just need a couple more lines, and you would be able to get it. And let me see. That's it. That's all the questions I have. Other than that, it's a really nice job, Marcio. So I appreciate you coming and presenting with us.
Thank you. Thank you.
All right. Let me go back here to my screen. And yes, guys, this is what you can do when you take our courses with us online, the ones that offer certificates. You need to come and present the project and on a real robot to get the certificate. So I encourage everyone to do what Marcio did here and present your projects with us because we're excited to see what solutions you come up with. That's it for us, guys. So thank you for watching, and thank you, Marcio. We'll see you guys next time. Okay, bye-bye.
Bye.